Hi, everybody. I hope you're all doing great. Today, this lesson is for Wednesday, March 25th. I'm recording it a little bit early, actually coming off of the superintendent's email that you guys won't be coming back on the 28th. Given the circumstances, I think it's probably a smart decision. I don't think it was very unexpected from anyone, but I just wanted to say I hope you're all doing well and stay healthy, stay safe, and let me know if you need anything. Anyways, I'm going to pause the video so we can get to the lecture notes, and then we'll go from there. Great. So as I mentioned, today's lesson is for Wednesday, March 25th. That means that homework 7 and in-class 7 will be due on Friday. So please try to submit those in the module on Blackboard or send me an email with photos or a PDF scan of those assignments. I'm definitely happy to talk about them in online office hours this week. So please use those as a resource. Exam 2 will be on Wednesday, April 1st. And since you guys definitely won't be here, I think the plan will be to post it on Blackboard early in the morning on April 1st. It'll be available for 24 hours. And I think, since you guys are going to be home, open note, but please, don't work with groups. Please make sure that all of the work is your own individual work and you're not consulting other resources. Other news is that we also just got approved for having VPN access, which is really excellent. I think we'll keep our learning objective with STAD the same, sort of just being familiar with the program, but using VPN, once you get an account, you should be able to log on to the system and your computer will think it's at USNA, so you could use STAD just like you did if you were in Bancroft. That being said, more details, I'll probably post a very short video on how we can log into VPN using your credentials. As I mentioned, today is the last lesson about API design criteria. Last time we finished example 1, we did the full example, axial compression, bending, shear, hoop, and combined checks. We found our column was safe. Today we're going to do another example, and my recommendation for today is to try to maybe pause the video once we set up the example and solve it on your own. And then go ahead, it's okay if you fast forward me and check your answers, or you can go ahead and kind of click through the video. If there's something that you want to watch slower, obviously take your time. But I would recommend definitely try to work the problem first on your own, and then have a look at the solution, have a look at these lecture notes once you've had a chance to do that. So let's go ahead and set up this example. So if you're following along with our notes format, this would be capital letter C of our new unit, which is API example 2. And fun fact, I was online the other day and I found out that the max depth in Lake Erie, so for anyone who's up around Pennsylvania, New York, is 210 feet. This is actually much shallower than if you were closer to Lake Michigan or Lake Superior, so another fun fact. But if you're in Lake Erie, the average depth in the central basin, so the central area, is only 60 feet. And you are the lead engineer. Oh, sorry, there we go. So you are the lead engineer designing a diving platform that will extend 5 feet above the water's surface. In the central basin. And the platform is expected to support a 20 kip axial load, a uniform lateral load of 0.2 kips per foot along the entire length of the submerged portion of the pile. and a 100 kip-foot moment applied at the platform as shown. So let's go ahead and just sketch these loads. So here's our pile. Here's the water surface, maybe here. This distance is 60 feet. This distance above the water is 5 feet. Maybe we have a platform on top. We're not so worried about what's on top. We're just worried about the loads that are being applied on this pile. And so we said we have a 20 kip load at the top of the pile. We have a 100 kip foot moment applied also at the top of the pile. And along the submerged water depth, we have a distributed load of 0.2 kips per foot. So here's our pile. I'll shade it a little bit. The steel pile with an elastic modulus of 29,000 kips per square inch, and F sub y is equal to 50 kips per square inch, has an outer diameter D naught equal to 45 inches and a thickness of 0.5 inches. For the load scenario shown, determine if the pile satisfies API design criteria. All right, and let's go ahead and let's just sketch our pile cross section too. So we said we have an outer diameter of 45 inches is equal to D outer, or D sometimes. And then our thickness is 0.5 inches, which means that our inner diameter is 45 inches minus 2 times our thickness, or 44 inches. All right, and we can also assume that it is affixed into the ground. That's the standard assumption. Unless I tell you that, assume that it's connected to the ground with a pin, you can always assume that it's fixed into the ground and free at the top. So let's go ahead and solve this problem. The very first thing we need to do is, given this loading situation, we need to find the maximum loads that the pile experiences. So P max, V max, and M max. So first we'll find P max, V max, and M max, which again, for something like this cantilever setup, this occurs at the end of the pile. And I can go ahead and I can say, okay, the sum of the forces in the y direction is equal to 0, which would equal my P max, my reaction here at the base of the pile, minus the 20 kip load in the y direction. So I get that P max is equal to 20 kips. Similarly, I can take the sum of the forces in the x direction equals 0. This will equal V max, my reaction, minus all of the x direction forces. So this would be that 0.2 kip per foot distributed load, which is distributed along the entire 60 feet of the pile, the submerged portion of the pile. Solving this tells me that V max is equal to 12 kips. And finally, if I sum the moments about the base of the pile, about A we'll say that this is equal to 0. This will be negative. We'll say that my moment is going to be clockwise because it's counteracting this moment and the moment due to this distributed load. So M max plus 100 kip feet is due to this point moment here at the end of the pile. We just add that. Plus 0.2 kips per foot distributed over 60 feet of the pile, and it is 30 feet. The resultant force would act 30 feet away from the pile itself. So doing that math, we get that M max is equal to 460 kip feet. So these are the loads that we'll use when we're calculating the actual compressive, bending, and shear stresses in the pile. The first check that we do is our axial compression check. So this will be step 2, is our axial compression check. And going ahead and stepping through, we have step 2.1, which is to find L sub E, which is equal to K times L. If I go and check out my table 61.1 in my Cliff Notes, it's the same criteria as the last example, but again, we have a built-in or a fixed end connected to a free end. Let's get this focused. Great, we have a built-in end connected to a free end, and so my K value is going to be 2.1. So from table 61.1, or you can use the table on top of that, we get that K is equal to 2.1. And that's because it's a fixed connected to a free. Those are my end conditions. So therefore I can plug this in. My total length is going to be 65 feet. Make sure that you remember that there's 5 feet of freeboard above the water surface. So we have 2.1 times 65 feet, which tells us that our effective length, L sub E, is equal to 136.5 feet. Great. So next we can calculate our actual slenderness ratio. So this is step 2.2, SR, which is equal to our effective length over the radius of gyration. Plugging in for the radius of gyration, we know that's equal to the moment of inertia divided by the area. So I can go ahead and calculate the moment of inertia for a pipe, which is equal to pi over 64 times d outer to the 4th minus d inner to the 4th. Plugging in numbers, pi over 64 times my outer diameter is 45 inches, taking that to the 4th power, minus my inner diameter of 44 inches, taking that to the 4th power. Plugging that into my calculator, I got 17,304.7 inches to the 4th. And my area, similar formula, we have pi over 4 times the outer diameter squared minus the inner diameter squared. So pi over 4 times 45 inches squared minus 44 inches squared. And I got that the area was equal to 69.9 inches squared. I can go ahead and plug these back in to this equation. So I get my effective length, which is 136.5 feet. My denominator is going to come out in inches. So I want to multiply this times 12 inches per foot to make sure that I have consistent units. And then I'm dividing this by the square root of my moment of inertia. So 17,304.7 inches to the 4th divided by 69.9 inches squared. And I get that my slenderness ratio for this beam is equal to 104.1. So we'll compare this later to the critical slenderness ratio to determine the type of pile we have. Next, we need to see if local buckling could be expected. So that's step 2.3, local buckling. And the first thing I do here is I check D over T, which is my diameter divided by my thickness, so 45 inches, divided by 0.5 inches, which is equal to 90, which is greater than 60. So therefore, I might have inelastic local buckling. And so I have this criteria with D over T greater than 60, where buckling might occur at the minimum of any of these three conditions with my elastic local buckling, inelastic local buckling, or my yield strength. So let's go ahead and calculate that. So therefore, I have buckling at the minimum of F sub XE, my elastic local buckling, equals 2C times E times T over D, which is equal to 2 times 0.3. That's a coefficient that will always be 0.3 for steel, times 29,000 KSI, times my thickness is 0.5 inches, divided by my diameter of 45 inches, which is equal to 193 KSI. Next, I have F sub XC, which is equal to Fy times 1.64 minus 0.23 times D over T to the 1/4. Plugging in numbers, we get this is equal to 50 KSI times 1.64 minus D over T we found was 90. So we'll take 0.23 times 90, the 1/4 power. Plugging all these values in, we get that F sub XC is equal to 46.6 KSI. And then finally, our yield strength is a given as 50 KSI. So our minimum in this situation is actually going to be F sub XC, 46.6. So therefore, min equals 46.6 KSI. And we'll use that moving forward. So what we do next is we calculate our critical slenderness ratio. This helps us determine whether we have a long and slender Euler column or an intermediate Johnson column or a short and stubby column. So C sub C, our critical slenderness ratio, is equal to 2 pi squared E divided by min. Plugging in numbers, we get 2 pi squared times 29,000 KSI divided by 46.6 KSI, which is equal to C sub C equals 110.8. So I'll start a new page for this because this is maybe going to take a little bit more space than we have. So given that information, we know that C sub C is 110.8. I'll zoom up. We have our slenderness ratio is 104.1. So we have step 2.5, SR equals 104.1, which is less than 110.8, equals our critical slenderness ratio. And we also have our slenderness ratio is 104.1, which is greater than 10. So if we go back and we look at our criteria, this classifies as an intermediate or Johnson column. So we have a slightly different equation than we used in the last example to calculate our critical buckling stress. So our critical buckling stress, P sub CR in this case, is going to equal the minimum that we calculated in step 2.3 times 1 minus our slenderness ratio squared divided by 2 times our critical slenderness ratio squared. Plugging in numbers, we get 46.6 KSI times 1 minus 104.1 squared over 2 times 110.8 squared. And so we get our critical buckling stress is equal to 26.0 KSI. That's our critical buckling stress. Our allowable buckling stress will be our critical buckling stress divided by a factor of safety. So our factor of safety equation from the Cliff Notes is equal to 5/3 plus 3/8 times our slenderness ratio over our critical slenderness ratio minus SR cubed over 8 C sub C cubed. Plugging in numbers here, we get 5/3 plus 3/8 times 104.1 over 110.8 minus 1/8 times 104.1 cubed over 110.8 cubed. And so our factor of safety is equal to 1.92. Pretty reasonable value. And finally, we have our allowable stress, which is equal to P sub CR divided by our factor of safety, which is equal to 26.0 KSI over 1.92. So our allowable axial stress is equal to 13.5 KSI. Once we have our allowable buckling stress, we can compare that to our actual stress. So let's go ahead and next we'll calculate our actual stress, little f sub a, which is equal to P max, the actual compressive load that we have on our structure, divided by our cross-sectional area, or 20 kips divided by 69.9 inches squared. So we have little f sub a is equal to 0.29 kips per square inch. And then finally, the very last step in all of these checks is to compare or to explicitly state that our actual compressive stress, which is equal to 0.29 KSI, is indeed less than our allowable buckling stress of 13.5 KSI, capital F sub A. So, okay, check. And we can move to the next check. After we do our axial compression check, we move right along to our bending check. Sorry, I'm getting ahead of myself. So next we'll do our bending check. Kind of step 3, big step 3. The first thing we do in our bending check is we compare the value d over t times f sub y, which is equal to 45 inches divided by half an inch, times f sub y is 50 KSI, which is equal to 4,500, which is greater than 3,000. So we have, again, these 3 conditions from our Cliff Notes. We have if it's less than 1,500, not our pile. If it's between 1,500 and 3,000, or if it's greater than 3,000. Remember, if it's greater than 3,000, or really always, we have to double check that d over t is not less, or that it's not greater than 300. So it must be less than 300. So we can go ahead and plug our numbers into this equation since we have the condition with d over t fy greater than 3,000. So therefore, our allowable bending stress is equal to 0.72 minus 0.58 times f sub y times the diameter divided by the thickness times the elastic modulus. That quantity times f sub y. Or plugging in numbers, we have 0.72 minus 0.58 times the quantity 50 KSI times 45 inches divided by half an inch times 29,000 KSI. That quantity times our yield strength of 50 KSI gives us an allowable bending stress of 31.5 KSI. And for completeness in this check, we also check the ratio of d over t of 45 inches over 0.5 inches. which is 90, which is less than 300. So, okay. This is, make sure you do this check. The next step is to find our actual bending stress. So little f sub b, which is equal to m max times the diameter over 2 divided by our moment of inertia. Plugging in numbers, we can look back to step 1. M max is 460 kip feet. Converting that so everything's in inches, we can multiply this times 12 inches per foot times our diameter, which is 45 inches, divided by 2. All divided by our moment of inertia, which we calculated in step 2.2, is 17,304.7 inches to the fourth. And so we get that our actual bending stress, little f sub b, is 7.18 KSI. And finally, the last step in this step is to compare. So we have little f sub b is equal to 7.18 KSI, which is less than 31.5 KSI equals our allowable bending stress. So we're okay. All right, chugging right along. After bending comes the shear check. So this will be step 4, our shear check. And the first thing we do is we always have our allowable shear stress is equal to 40% or 0.4 times our yield strength, or 0.4 times 50 KSI equals 20 KSI. That's our allowable shear stress. Our actual shear stress, little f sub v, is equal to our max shear felt by the pile divided by 0.5 times the cross-sectional area. So again, looking back to the very first step where I calculated V max using statics, that was 12 kips divided by 0.5 times 69.9 inches squared. And so we get little f sub v is equal to 0.34 KSI. And last part, we get little f sub v of 0.34 KSI is much less than 20 KSI, or our allowable. So, okay. And we can move on to our hoop stress. All right, 2 checks left. So next we'll do our hoop stress check. Remember that hoop stress is due to the pile being submerged. It has this hydrostatic pressure acting over the entire surface of the body. And so we have to check for this the stress. So first we'll calculate our geometric shape parameter m, which is equal to L over D times the square root of 2D over T. Plugging in numbers and being careful with units, my total length of the pile is 65 feet times 12 inches per foot. Remember to use the length, not the effective length here. And we're dividing that by our diameter of 45 inches times the square root of 2 times 45 inches divided by our thickness is 1/2 inch, which is equal to 236.2 is our M value. If we want to see what situation we have M divided by D over T, which is equal to 236.2 divided by divided by 45 over 0.5. Both of those units are in inches. So 236.2 divided by 90 is equal to 2.6. I can check out my Cliff Notes. So we have these 5 situations. these 5 situations. And we're in the very top situation. So 2.6 is greater than 1.6, which is m divided by dt. So the equation that we'll use for our hoop stress coefficient is 0.44 times t divided by d. So just to put this in the notes, we have this is greater than 1.6. So m is greater than 1.6 times d over t. And therefore, our hoop stress coefficient, C sub h, will equal 0.44 times t over d, or 0.44 times 0.5 inches over 45 inches. And we get our hoop stress coefficient is 0.0049. We can use this to find our elastic hoop stress. So F sub HE is equal to 2 times our hoop coefficient times our elastic modulus times our thickness divided by the diameter, which is equal to 2 times 0.0049 times 29,000 KSI. Our thickness is 1/2 inch divided by 45 inches. And we get that F sub HE is equal to 3.15 KSI. Next, we need to see if this elastic hoop buckling stress is our critical hoop buckling stress, or if we have to modify this value. So let me adjust the view slightly. All right, so next we'll compare, this is 5.4, F sub HE to FY. So if I divide 3.15 KSI divided by 50, KSI is equal to 0.06, which is less than 0.55. So since I have this condition of F sub HE divided by FY less than 0.5, I might have elastic buckling. So my critical hoop buckling stress is the same as my elastic hoop buckling stress. So therefore, F sub HC equals F sub HE, which is equal to 3.15 KSI. Okay. Next, I need to compare this to my actual hoop stress. So this is step 5.5 to find little f sub h, which is equal to my hydrostatic pressure at the bottom times my diameter divided by 2 times my thickness. I can calculate pressure using the unit weight of water times my depth of my pile, and multiplying that by my diameter divided by 2 times the thickness. For my unit weight of water, since I'm in Lake Erie, let's go ahead and use fresh water. And so we'll get 62.4 pounds per feet cubed times my depth is 60 feet. Let's do some unit conversion. So I have 1 foot squared divided by 12 inches, that quantity squared, or 144 inches squared. That gets me into pounds per inches squared. Times we have 1 kip is 1,000 pounds. That gives us in kips per square inch. That's the units we like. Times our diameter is 45 inches divided by 2 times our thickness of 0.5 inches. Plugging all these numbers in, we get that F sub h lowercase is equal to 1.17 KSI. And so the final check for our hoop stress, step 5.6, is to check whether our actual hoop stress is less than our critical hoop stress divided by a factor of safety. Typically, factor of safety equals 2. We didn't say that there was any storm or special scenario here. So let's go ahead and check that 3.15, so F sub HC over factor of safety of 2 will equal 3.15 KSI over 2, which is equal to 1.58 KSI. This is indeed greater than our actual hoop stress of 117, or sorry, 1.17 KSI, lowercase f sub h. So we're okay. And we can move on to our final combined stress check. So this is the very last step, step 6, our combined stress check. And again, here we're considering the combined effects of axial compression plus bending. Specifically, the first thing we need to do is see whether the P delta effect is important, whether that compressive load is so heavy that you might cause additional bending to occur. So we'll check the ratio of our actual compressive stress to our allowable, capital F sub A, which is equal to 0.29 KSI. I can go back and double check that from my step 2, my axial compression check. And my allowable is equal to 13.5 KSI. This is equal to 0.02, which is less than 0.15. So we don't expect any P delta effect, which is good because consulting the Cliff Notes, that means that we only need to do one check. So again, we have these 3 different situations. If the P delta effect is important, if this value is greater than 0.15, we have to do 2 checks. If not, we only have to check that the ratio of our actual to allowable axial and bending stresses added together are less than 1. So let's go ahead and check that. We have, therefore, check that little f sub A over capital F sub A plus little f sub B over capital F sub B is less than or equal to 1. And plugging in numbers here again, I can say 0.29 KSI over 13.5 KSI plus, if I look back at my bending stress check, my actual bending stress was 7.18 KSI. My allowable bending stress was 31.5 KSI. Adding these together is 0.25, which is less than 1, so okay. And therefore, the final answer is that we pass all API design criteria. And so this is the final answer, but as a design engineer, just something to keep in mind is that this might not be the last step. So maybe you say, oh, wow, this passed every single check with flying colors. Could we, for instance, reduce the outer diameter, keeping the thickness the same and maybe save some money on installation, steel costs, material costs, et cetera. So that's kind of why design is such an iterative process, because you can always try to optimize something for safety, for cost effectiveness, ease of construction based on what you have in the shed, etc. Anyways, that's all I have for you guys today. Looking forward to seeing you all in office hours. I hope you have a fantastic day and looking forward to talking soon.